So hi there. I'm going to present some work that I've been doing on developing new machine learning tools that can help you understand disease subtypes and their longitudinal progression. And I'm going to work out how this works. Yes. Okay. So neurodegenerative diseases are temporally heterogeneous. So individuals are a range of disease stages at which they have different spatial patterns of pathology. And these spatial patterns can look very different at different disease stages because the pathology tends to begin focally in one region before spreading to other regions. They're also phenotypically heterogeneous, so individuals have different disease subtypes that have different spatial patterns of pathology. So this combination of phenotypic and temporal heterogeneity produces cross-sectional heterogeneity in atrophy patterns. So what we can imagine is that we have some underlying disease process that consists of a set of subtypes that have different patterns of progression over time. And then if we're to sample individuals cross-sectionally from this underlying process, what we'll observe are individuals that have a range of different disease subtypes and that are at different stages. So this leaves us with a highly heterogeneous data set from which it's difficult to disentangle the underlying disease process. And importantly, this heterogeneity can dilute or obscure progression patterns if it's not analyzed carefully. So for example, if we were to use a simple technique like regression against clinical diagnosis, what we'd end up with is a model that has just a few stages, where each stage is just the average of individuals within that diagnosis group. So this misses the hidden detail of the underlying disease subtypes and their progression patterns, which limits both our understanding of the underlying disease process as well as our ability to stratify individuals by both subtype and stage. And this potentially has important consequences in clinical trials because we may be unable to identify the group in which a treatment would be most effective. So machine learning can be used to disentangle this heterogeneity. However, typical machine learning approaches only disentangle one aspect of the heterogeneity. So one example is disease progression modeling, which aims to disentangle temporal heterogeneity by reconstructing the progression of a disease from either cross-sectional or short-term longitudinal data sets. But it assumes that all individuals undergo the same progression, so it doesn't tell us anything about hidden disease subtypes within the data. On the other hand, we have clustering methods, which aims to disentangle phenotypic heterogeneity by associating individuals with similar biomarker values. But they don't describe the underlying disease process. They're unable to tell you anything about how the disease evolves. So we've developed a new machine learning tool called Subtype and Stage Inference, which integrates ideas from both clustering and disease progression modeling, allowing you to reconstruct the underlying disease subtypes and stages from heterogeneous patient snapshots. And once you have this type of model, you can use it for subtyping and staging of new individuals simply by comparing their data to the reconstruction of the disease subtypes and their progression patterns. In fact, you can reconstruct these type of progression patterns from purely cross-sectional data. So I'm just going to illustrate simply how you can do that intuitively. So let's imagine that we have a simple progression pattern in which the frontal lobe atrophies before the temporal lobe. And now we take cross-sectional samples from this data set. What we'll observe is that there are some individuals that have just frontal lobe atrophy. What we don't have in our data set are any individuals with just temporal lobe atrophy. So we can use this idea to infer that frontal lobe atrophy precedes temporal lobe atrophy in the progression pattern. And we can extend this idea to subtypes. So now if we have two different progression patterns, one in which the frontal lobe atrophies before the temporal lobe, and the other in which the converse is true, what we'll observe now if we take a cross-sectional sample of individuals is that some individuals have just temporal lobe atrophy, but that we also have individuals with just frontal lobe atrophy. And from this, we can infer that there are two different progression patterns, one in which the frontal lobe atrophies before the temporal lobe, and another in which the converse is true. So we can encode this idea mathematically using a Bayesian model, where we have a hidden subtype and a hidden stage variable. And we can describe the evolution across the different stages of the disease using a trajectory model. In this case, we use a piecewise linear model where we index the stages as a sequence in which biomarkers reach different z-scores relative to a control population. And we can then infer what the progression pattern of the different subtypes is by simply optimizing the parameters of our trajectory model to best match our data set. And we can further infer the optimal number of subtypes by using information criterion. So I'm going to talk about two studies in which we've applied sustain. So the first is in genetic frontotemporal dementia. So in genetic frontotemporal dementia, there are different genetic groups that have relatively distinct atrophy patterns. So carriers of mutations in microtubule-associated protein tau, or MAPT, tend to have more focal temporal lobe atrophy compared to the characteristic frontotemporal pattern associated with frontotemporal dementia. Carriers of mutations in progranulin tend to have more frontal lobe atrophy, and their atrophy pattern tends to be more asymmetric. And carriers of mutations in chromosome 9 open reading frame 72, or C9orf72, tend to have more widespread atrophy that affects the frontal and temporal lobes more equally. So we can use data from genetic frontotemporal dementia to test the ability of sustain to recover subtype progression patterns by basically pooling together data from individuals with any of the different types of mutation, fitting the model to this data set, and then comparing the outputted different subtype progression patterns to the actual assignment of the different mutations. So we use data from the GEMFI dataset with data coming from 172 carriers of mutations in progranulin, MAPT, and C9orf72. And the biomarkers used in the model were regional free surfer volumes, as well as a measure of asymmetry. And we measured these volumes as Z-scores relative to a control population of 141 individuals that didn't carry any of the mutations. So fitting the model to data from all mutation carriers without providing any information about the different mutation types, what we find is that there are 4 different phenotypes in the data set. So here, each row is a different subtype, and the stages going from left to right. And each region is colored according to its Z-score, with a Z-score of 1 in red, 2 in magenta, and 3 in blue. And in the bottom corner of each of the little pictures, you can see a circle, and that indicates the asymmetry of the progression pattern. So as we'd expect, we find that the asymmetric frontal progression pattern is mainly associated with the progranulin mutation carriers. The more temporal progression pattern is associated with carriers of mutations in MAPT. However, we find that both the frontotemporal and subcortical progression pattern are associated with, tend to be contributed to by carriers of mutations in C9orf72. So this suggests that this group is both heterogeneous, but further that it consists of 2 distinct subtypes, one that has a more frontotemporal atrophy pattern and the other with a more subcortical pattern. So we next looked at the ability of the model to discriminate subtypes and stages. So here I'm looking at the different subtypes and their identifiability in different diagnostic groups, so unaffected individuals, unaffected individuals. So here, the triangle plots show the probability an individual belongs to a particular subtype. So individuals in the middle of the triangle have a approximately equal probability of belonging to each progression pattern, and individuals in the corner of the triangle are strongly assigned to a particular phenotype. So what we see is that, particularly in the affected carriers, is that individuals are strongly assigned to a particular phenotype. And you can use these phenotypes from the sustain model to discriminate an individual's genotype. So we have 93% of the carriers of mutations in progranulin being assigned to the asymmetric frontal subtype, 91% of the MAPT carriers being assigned to the temporal subtype, and 75% of the C9orf72 mutation carriers being assigned to either the frontotemporal or subcortical subtype. And we compared this performance to if you just look at a subtypes-only model, so a standard clustering technique which doesn't account for the temporal progression. And what we find is that sustain outperforms this type of technique, giving a balanced accuracy of 86% compared to 69% using clustering. So we also looked at the distributions of the stages in different diagnostic groups. So here, the graph shows the probability of an individual belongs to a different stage in the model. And what we see is the unaffected carriers in blue tend to be at early stages, whereas the affected carriers in yellow tend to be at later stages. So next I'm going to talk about the work that we've done in Alzheimer's disease. So in Alzheimer's disease, there are three pathological subtypes that have been identified at late stages and are visible on pre-mortem MRI, which have been called a typical subtype, a hippocampal sparing, and a limbic predominant. But the temporal progression of these subtypes is not well characterized. And so we applied the model to Alzheimer's disease to see whether we recovered the same subtypes and also to characterize their temporal progression, in particular the earlier stages. So we've looked at data from two different data sets with both from ADNI using volumetric MRI at different field strengths. So here I'm just going to look at the data from the 3T data set, as the 1.5T just confirms the findings, basically. So we've looked at regional free surface volumes, which again we measured as Z-scores relative to a control population. So here our control population was amyloid negative, cognitively normal subjects. And the 3T dataset has 793 subjects, 269 cognitively normal, 407 with MCI, and 117 with Alzheimer's disease. So what we found was that SUSTAIN identified three different Alzheimer's disease progression patterns. So here again, each row is a different subtype, and going from left to right are the different stages of the model, with the regions being colored according to their Z-score, with 1 in red, 2 in magenta, and 3 in blue. So we've termed these different subtypes as a more typical subtype, more cortical subtype that tends to have more kind of cortical involvement earlier in the stages, and a subcortical subtype with involvement of subcortical regions at earlier stages. So what we can see is that these kind of reflect what we've seen in neuropathological studies, but we can characterize the full temporal progression. So we then looked at the ability of SUSTAIN to assign individuals to subtypes and stages, as we did for GEMFI. What we find is that the SUSTAIN subtypes become more identifiable as the disease progresses. So again, these triangle plots show you the probability an individual belongs to a particular subtype, with individuals in the middle having equal probability of belonging to any subtype and individuals at the corners being strongly assigned. And so what we see is that in the Alzheimer's disease group, we can see that individuals are strongly assigned to a particular subtype. Interestingly, in the MCI group, we can see that there are kind of a subset of individuals that are strongly assigned, as well as some individuals which can't be assigned to a particular subtype. So we then looked at the distribution of the stages assigned by the model. So here we're looking at the probability that individuals belong to different stages. And what we see is that the cognitively normal subjects in blue tend to be at the earlier stages. The Alzheimer's disease subjects in yellow tend to be at the later stages. And the MCI subjects who are in teal tend to be kind of more in between those two categories. So we further looked at the ability of SUSTAIN for predicting longitudinal risk of conversion from MCI to Alzheimer's disease. So here I'm showing Cox proportional hazards models that tell you the estimated probability of remaining MCI depending on your baseline SUSTAIN subtype and SUSTAIN stage. What we find is that both the subtype and the stage provide added information about your risk of conversion. So individuals that are assigned to the typical subtype have a higher probability of converting from MCI to Alzheimer's disease compared to the subcortical subtype who have the slowest conversion. And individuals with higher SUSTAIN stage also have a higher risk of conversion from MCI to Alzheimer's disease. And we further compared this to if you fit a model that just has either disease subtypes or just has a progression pattern, and found that it outperforms both of those types of models for looking at risk of conversion. So I will just conclude very quickly. So in genetic frontotemporal dementia, we validate the ability of sustained to recover subtype progression patterns, further finding that carriers of mutations in C9orf72 are heterogeneous, consisting of 2 subtypes. In Alzheimer's disease, we find 3 subtypes and characterize their temporal progression. And in both diseases, we demonstrate the utility of sustain for patient subtyping and staging, as well as that sustain can outperform models that don't account for heterogeneity in either subtype or stage. Several things that are interesting to consider for future work that can further improve the stratification of the models, accounting for mixed pathology, and having more individualized models that can incorporate even more heterogeneity in the different groups are just 2 of some interesting opportunities. So finally, I'd like to thank my co-authors and funding bodies. This work is available on bioRxiv, and we also have 2 further applications that are being presented at conferences later this year. One is looking at genome-wide associations with these different subtypes, and another is in lung disease. Thank you. That's it.